Okay. All right, well, thanks, Brian, for the introduction, and thanks to, is this okay? To Gretchen and Trey for the invitation. What I want to use my time for today is to tell you about a project we've actually been having a lot of fun with at UCLA, where officially we're trying to sympathetically cool molecules with laser-cooled atoms. And I'll tell you about that at the end of the talk, but the questions I want to answer are probably more plain than that today, or the things I want to tell you about it. And that's really, what can you do with these hybrid atom-ion traps that we're building, and why did we get in this game to begin with? My attempt to answer these questions are here, and I'm going to start off by doing something really inexcusable. And so I asked my students to plug their ears. I'm going to skip the motivation completely in the interest of time. Suffice it to say that we're excuse me, interested in making cold molecules. And my motivation for that are what I call the big four, which is quantum simulation, quantum computation, precision measurement, and quantum chemistry. And my problem is I'm a little bit ADD in that I want to do something in all those things. And so we wanted to take a step back and develop a more general cooling technique that would actually allow us to change molecular species and go do a precision test of physics and then go do some quantum chemistry. And so that brought us to the idea of sympathetically cooling molecules, where I'll start the talk. I think you're all familiar with this from John Bone's work. What I want to point out to you is that if you're really trying to do this at ultra cold temperatures, you run into some problems pretty quickly. And I'll point those problems out to you and then argue that charged molecules solve both of them. And then I'll spend the meat of the talk telling you about what we've actually done in the motion trap. So that's what we call this hybrid trap, and you'll see why. And there are three main efforts here. The first is in what I would call plasma and non-equilibrium physics. The second is in quantum chemistry. And the third is making cold molecular ions. Now, I'd like to tell you that we set out with the goal of measuring all three of these things. But to be honest, we set out with this goal and had to address these things along the way. They just happened to us. All right. And our work is funded by the Army Research Office and the NSF, and we're really grateful for that. Before I get started, let me tell you the people that actually do the work. Christian, Stephen, Kwong, Wade, and Scott had their hands in almost everything I'll show you. Alex is a new postdoc who helped out a lot with some of the chemistry I'll show in the middle of the talk, and it's all centered on a very fruitful and necessary collaboration with Svetlana. All right. Okay, so sympathetic cooling. Let me start off with an example you're probably all familiar with. You have something you want to cool down. You have something that's cold that you can use to sympathetically cool that, and you put it in a glass, right? So you have to have something to hold it. And so the analogy to the cold molecule world is really one-to-one, right? The whiskey, well, that's your molecules, right? That's the thing you want to cool down. The ice cubes are, of course, laser-cooled atoms. So maybe a magneto-optical trap, or maybe you'll have a BEC, right? But you get to the glass, and there you have a problem, because you don't have a glass, right? For neutral molecules, with sort of lab-sized electromagnetic, magneto-electrostatic fields, about the best you can do is a potential of maybe 10 millikelvin, maybe a Kelvin in special instances. So you're in this weird sort of catch-22 situation where you need to cool these molecules down so you can hold on to them, but you can't hold on to them until you cool them down, right? If you agree to work with charged molecules, though, it's a completely different story, right? 1 volt is 10,000 Kelvin. So with a molecular ion, you have a glass, and that's an ion trap, right? So that's the first reason that pushed us in this molecular ion way. The second problem is what I call the vibrational problem, and this is best illustrated from John Doyle's work, I think. So John, as you know, does sympathetic cooling of neutral molecules with helium. And in that work, what they find, you can't really see here, so I'll just tell you, is that maybe 1 in 100 million collisions actually relaxes the vibrational degree of freedom, right? So we need to cool down the rotation of the molecule, the vibration, and its movement. So helium is great at cooling down the motion, the translation, and the rotation, but it just doesn't touch the vibrational degree of freedom. All right. You may say, well, look, I know thermodynamics always wins. Ion traps have long lifetimes, so let's just wait it out. All right, but we don't have the nice advantage that John has, which is that his black body radiation is at his buffer gas temperature, right? Everything's cryogenic. We're not going to get a chamber that's at, ultra cold temperatures, right? We're never going to have a black body radiation of a microkelvin. So we actually have to beat back this competing reservoir. And so we argued in 2009 when we started that because of this neutral ion interaction, you're going to get near unit relaxation efficiency for these collisions, and we'll talk about that at the end. All right, so now let me tell you about the trap, how we actually build it. It's a simple MOT and an ion trap. We take them and shove them together. When you do that, it spells the word motion. I'll show you that again. So it's named the motion trap. It wasn't too hard. So this isn't, of course, the only way to make cold molecules or molecular ions. And I want to point out that Michael Drusen and Stefan Schiller some years ago showed a way of using atomic ions for sympathetic cooling plus rotational state optical pumping with a couple of lasers. And more recently, and very excitingly, our own chair, Brian Odom, has developed a new technique using pulse lasers, which works really efficiently, it's very quick, and it looks applicable to a lot of molecules. So I think there's a lot to come here still. All right, so what does our system look like? It's just a standard Paul trap. If you look in the middle of it, in this case, we've loaded ytterbium ions into just some sort of 2D crystal or 3D crystal here, and they're immersed inside of a calcium MOT. We chose calcium because of its low mass and its reduced reactivity, and those things we'll talk about more as we go. Now, the great things for someone like me who's a molecule person moving into this ion world is that people like Dave Wineland, Rainer Blatt, and others have shown all these beautiful techniques, like we can just load in single ions into our ion trap and image them, and we can give them all names and watch what happens to them. Right? But for us, unfortunately, we're working with molecular ions, and those, in this case, would be these little dark spots, right? So we need a robust way of identifying them. So here, to be honest, I've sort of lied to you. These are all just ytterbium isotopes, and so the dark spots aren't molecules. But the point is the same, is how do you identify these molecules or these ions robustly? And there are a lot of techniques for doing that, but we found that either we didn't know how to use them or we ended up lying to ourselves a lot. So we added this thing to the experiment, which is a time-of-flight mass spectrometer. And it's radially coupled, and that's very important. And Stephen was really the first to pull this off and make it work. And when Christian joined our group, he took it to the next level so that now we have complete isotopic resolution of basically everything in the trap. So we can load up a chain like this, hit a button, and then we get a mass spectrum now, where these are the, in this case, it's just ytterbium isotopes, and you can see here's 174, 173, they're all in there. Right? And I point this out because, one, it was really, really hard, even though it doesn't sound like it, and two, this is really important to almost everything I'm going to tell you as we go along. It's been a really great tool for us. All right. So we didn't jump straight to cooling molecular ions, right? We first started off, as I've shown here, with the ytterbium ions immersed in a calcium MOT. And that allowed us to make sure that we could overlap the traps, get them running together, work out all the bugs. But it also gave us something we didn't really expect, and that was some plasma/non-equilibrium physics. So let me show you what I mean by that. This is probably the first bit of data we actually ever took in the experiment. And we were trapping ytterbium ions. We scan a weak probe laser across and look at the Doppler fluorescence. With no MOT, no laser cooling, you see that the ions that are about 800 Kelvin. That's about what you'd expect. So we turn on the MOT and expect to see all this great sympathetic cooling, and they cool down to about 600 Kelvin, right? So I stole a word that John Bone used in other contexts. It's not sympathetic cooling, it's simply pathetic cooling. Right? But we know that thermodynamics wins, right? It always wins. We know we have a reservoir at a millikelvin, so something must be going on. And that is other heat loads, right? And those heat loads we now understand, and we've tried to coin this phrase of micromotion interruption. And what it is the ions in the trap, they're undergoing some thermal motion, they're undergoing driven micromotion. And if you have a collision with the ultra-cold atoms or even with the other ions, you can couple energy in from the RF field. All right? So let me illustrate that to you with what I call a stopping collision. So this is a normal harmonic oscillator, so just a ball rolling in a bowl, no micromotion. As you know, it's some sinusoidal oscillation. If I have a collision here that stops it, right? That's the ultimate cooling collision. The trajectory going forward is just a cosine with that amplitude, and that t equals 0, right? So in an ion trap, you don't have sines and cosines. You have Matthew signs and Matthew cosines, and they have a stopwatch, right? They have some knowledge of the RF phase. And so although you may have a trajectory that looks very similar, you see there's some sinusoidal thing with the micromotion on top. if you have a collision, most of the time it's cooling, right? The amplitude's reduced, energy's removed. But occasionally, if you collide at the wrong time, you can actually come away, even though you're momentarily stopped, with more energy, right? And so how is that possible? Well, basically that wrong time is a moment when the Matthews signs and cosines know that the micromotion velocity needs to be large, right? And so if that velocity is large, the only way the particle can be stopped is to have an oppositely directed thermal velocity that's very large, right? And so the RF trap then just heats this thing up. You just couple energy in. So this is very important to us. We spent a lot of time working on this, and student Kwong Chen really pioneered this. I'll just show you basically that these equations exist. I don't want to really talk about the details, but we've now developed an analytical theory that completely explains this at the level of understanding both the average energy and the dynamics, the relaxation rate, and its dependence on all the trap parameters and masses and whatnot. And the rules of thumb aren't different than what was known within the community, I would say. That's, you want a low buffer gas mass, you want a low Matthew Q parameter, but we can be more specific about what the limits are of our cooling. But it turns out this actually isn't the most dominant effect. The most dominant effect, and the thing that really caused the simply pathetic cooling, is what you might call ion-ion collisions. So, clearly the ion interacts with the buffer gas, but it's also interacting with other ions in the trap, right? And that can couple in energy. So using the same treatment as I've shown you before, you can arrive at an equation like this for the heating rate of just ions in a trap. And again, don't worry about the details. It just depends on things like the density and the temperature and trap parameters. One parameter you may not have seen before, though, is this natural log of lambda. This is the Coulomb logarithm, and it comes from plasma physics. Because when you're dealing with scattering of charged particles, you're going to end up with an integral of 1 over r. And that's problematic on both ends, right? It blows up on the short range and at the long range. Landau was the first to really look at this, and he said, well, it's not so bad. On the long range, there's a Debye length. On the short range, there's some distance of closest approach, right? So you just cut it off, do the integral, you get the natural log of this ratio. And let's just call it lambda because it's probably not really that, right? And so there's a cottage industry in plasma physics of just trying to figure out log lambda, because if you can figure that out, you can, do sort of easier predictions about things like, thermonuclear ignition, right? Really important problems. And for a long, long time, the state of the art was, well, it's not that, it's about 3/4 of that, right? And Landau and Spitzer are probably most responsible for that. In 2008, a Los Alamos collaboration using the giant supercomputers behind the fence simulated a plasma and said, well, we can make this a little bit better by adding 1 to it, right? So it works for a little bit more strongly coupled plasma. So if you're an ion trapper, the plasma physics G is basically R gamma, which is the ratio of potential to kinetic energy. The bigger it is, the more strongly coupled the ion trap or the plasma is. So we knew we couldn't quite use these in the ion trap because of some peculiarities with the trap. But we knew that we also knew everything else in here. So we just turned it around and did a measurement of this natural log lambda. And that's what's shown here as a function of gas, liquid, and solid phase of the ion trap. And this is log lambda. And you see there's a huge range. So our measurement agrees with the plasma physics measurement where it has to, which is in the gas phase. As you become more strongly coupled, basically this treatment breaks down and we absorb error into the definition of log lambda. But that's okay because log lambda is often situationally dependent if you're not careful. And what makes it even better is that so far it looks like this definition of log lambda, which we've just parameterized here, is universal in every ion trap we've looked at. So we can use this now to write down this heating rate. All right. So, before I forget, I should say that I saw Tom Killian wandering around here, and he's our local AMO expert on log lambda. So if you have questions about it, you should corner him before he leaves. So with these two things, though, we've got to the level, I think, where we solve the problem of the average energy, its steady state value, and its dynamics. And now we're looking at, can we go beyond the second moment, right? So the energy is the second moment of the distribution. And what got us thinking about this was a paper by Ralph DeVoe in 2009, where he was cooling barium ions in a buffer gas. It was all simulation. And this is the probability distribution for the position that he found as a function of buffer gas mass. So this is helium, and out here is xenon. And he saw this power law tail develop in the distribution, and he empirically fit this formula for that power. It's just 4 over the mass ratio minus 1. So using the same treatment as before, we could write down, we could treat the collision process as basically a random walk in energy space, more or less. And what you find when you do that is you get an additive part, which is what you normally get in thermodynamics, right? That gives you Gaussian statistics, central limit theorem, Maxwell-Boltzmann things. But you also get a multiplicative part. When you get a multiplicative part, you get power laws. And so using ideas that we learned from finance, but are certainly much broader, we were able to estimate what this power ought to be, and it's pretty close. So this got us thinking about going beyond the second moment a little more, and we enlisted some local statistical physicists at UCLA, Alex Devine and his student, Christian Vaca. And I'll just say like 2 words and move on because this is still very preliminary, but we're quite certain there's going to be the ability in ion traps to observe really some interesting off-equilibrium physics. We can see distributions here which were incredibly non-Maxwellian. We actually think you should be able to see the fluctuation dissipation theorem breakdown in the right instance. And I think this is probably fairly important, at least the feeling I get from the statistical bio people I know, because they don't have very many nice controllable environments to simulate and to understand off-equilibrium physics, right? All right, but more to come on this. All right, so once we got that understood, we moved on to what I would, to the next sort of challenge we faced, which was some quantum chemistry. And the signal of that was we had an ion chain within the MOT, and we would see them sort of just one by one go away, right? And this wasn't terribly surprising because we knew these things could react. We knew that calcium could collide with the ytterbium, and ytterbium wanted its electron more, right? And so we had to learn how to control this and understand it, so we launched sort of an investigation into it. And though I just sort of faked the data here, the real data looks pretty similar. So we have an ion chain, and you watch it just sort of slowly go away one by one. And then you can extract some signal and some reaction rate from that. But it's a little complicated by the fact that since you're laser cooling, the ions are spending different, their time in different quantum states. And so if you really want to extract the reaction rate of the individual quantum states, you have to play some games. Unfortunately, even though the ion crystal is changing a lot in size, if you look at the fraction of the time, and this is just a measurement based on the fluorescence, that each of these ions stay in the P state, it's very constant over the course of the reaction. So then by just changing your laser intensities into tunings, you could do things like watch this reaction rate as a function of, in this case, fraction in the P state. And you see there's a small slope there, which tells you that entrance channel's reaction rate. You can do the same thing with the D state. One of the things that we had trouble with for a long time, though, was understanding this y-intercept. What is the reaction rate of the S state? Because you can't just keep turning your laser intensities down, your laser cooling stops, the ions heat up, and nothing works anymore. But having this time of flight solves this problem completely for us. So we can instead look at the mass spectra. So you see there's some calcium ions, there's the ytterbium ions. If these molecular ions were being made, they would be here in the reaction. If we zoom in, you can see all the isotopes here of ytterbium in this case. And so what we decided to do was we laser cool only 172, and then all the other guys are just in their S state, but they're also cold and immersed in the cloud. And using the TOF, we just watch them react away, right? And so in parallel, we can see all these isotopes reacting away. You can isotopically resolve the reaction rate, and it's just plotted here. So with that, we can do things like, quantum resolve the entrance channels and tell you their reaction rates, right? So this was just one example of some of the work we've done here, the other references, but more importantly, a lot of other groups have done some beautiful work here. I think Vladen's group was the first. The next speaker did some beautiful work in rubidium and ytterbium. Wynn Smith, who is here, has done some great work in sodium. And Stefan Village has done some beautiful work with even large molecules here with ions. All right. So with those two things understood and the ability to control them, we then moved on to our main goal, which was actually making cold molecules. And what we learned from that taught us what we had to do. And that was, well, we replaced the ytterbium with barium because the ytterbium just reacts way too quickly. And we use that to sympathetically cool the molecular ion that we want, which is barium chloride. And this takes care of the translational motion, right? So this beats back all those ion-ion heating problems. And then we immerse it in a calcium mott to cool the internal degrees of freedom, right? And so the question is, does it work? Well, translationally cold, yes. People like Mikhail Drusen have basically been doing this for a decade. The internal states, though, are the real problems. Thanks, Mark. And so to measure the internal state population, you obviously want to use spectroscopy, right? You have some large row vibrational distribution, you cool the molecule down, and you see just a few spectroscopical lines, and you extract an internal temperature. But that's a problem if you know about molecular ions, because there's basically no spectroscopy. In fact, when we started the project, we only knew two things, and that was that there was an estimate that this molecule would dissociate with an energy of about 38,000 wave numbers, and that when it dissociated, we'd leave behind a barium ion. So we got a laser, we turned it to 38,001, and just tried to blow this thing apart and see barium ions. We had to keep going up from 38,000, but eventually when we got to sort of the 40,000s, we saw it, right? So this is just a broadband photodissociation cross-section of this molecule. We turned, at this point, to Svetlana Katochkova, who calculated the first ever molecular structure of the molecule. And so, well, what you're doing is it's a singlet sigma ground state, and it's a repulsive singlet pi, and you're just dissociating there. And that was nice because it gave us the potentials and these constants, but we were a little disappointed at this point because this is incredibly broad, right? It's sort of 4,000 wave numbers broad. And so we thought it would be impossible to get any temperature information about the internal degrees of freedom. You can see that if you look at the the individual cross-sections of the different vibrational states. So this is V equals 0, here's V equals 1. Our data is, some thermal average of it with a few others. So even if you cooled all the way to 0 Kelvin, your cross-section changes from what it is here to the blue line, right? So that's sort of, many orders of magnitude of cooling and sort of a slight change. But we were staring at it one day and realized that because of the node in the V equals 1 cross-section, which is due to the node in the V equals 1 wave function, that if we tuned a laser right here, we would only dissociate V equals 0. Conversely, if we tuned a laser over here, we would primarily dissociate V equals 1. So if the mott really cools these things, we should see an enhancement here, and we should see a suppression here. And if you put it together, you expect to see something like this. No cooling, you get a flat line. 100% in the ground state, you get a green line. And then 90% is the red line. And the data we took sort of fell in between 90 and 100%. Now, the value of this isn't incredibly impressive. And you can see why. I mean, this was in the early days when we didn't have good control, and the ions are barely even in the mott most of the time. But what is interesting, though, is this the relaxation rate that you extract from this vibrational quenching cross-section, is something of order Langevin, right, which is basically the elastic collision rate. So almost 1 out of every 5 collisions is relaxing the internal degrees of freedom, right? Compare that to the 1 out of 100 million that you get in the neutral world, right? And so up until last week, I sort of had to start hand-waving now to explain this, or I would just end my talk. But Thierry Stocklin at ISM in Bordeaux took it upon himself to actually calculate this, this collision problem, and he just shared his results with us. So he first started by calculating these potential energy surfaces for the calcium barium chloride complex, and this is the surface with barium chloride at its sort of equilibrium geometry. So on its own, it has about a 5 Bohr radii bond length, and then the calcium atom comes in with some R and theta plotted here. And so you have a minimum of potential about the way I've drawn it here at about 9 Bohr radii and 120 degrees. But this is not the minimum of the complex. The minimum of the complex is significantly different and is shifted inwards, and the angles change a lot. And most importantly, this bond length has stretched now, right? And so this is about 1,000 Kelvin deeper. And so you see that the calcium atom coming in is very strongly coupled to the bond length of the molecule, right? And so he had calculated these a few months ago and sort of expected, okay, this is why, right? This is, you have this coupling to this bond length, so there's going to be a large relaxation right here. But just last week, he actually finished what was a tour de force of computational physics and calculated the relaxation rate of V equals 1 with a calcium collision. And what he finds at our temperatures is basically, it's sort of scarily close to what we measured, so about 10 to the minus 9 cubic centimeters per second. And the good news is we think this is pretty general, so it should work with a large class of molecules. All right. So with that, I think I'm out of time, and let me just summarize. Hopefully, I sort of skipped the part where I told you molecular ions were great, but hopefully you'll trust me. Told you about the motion trap. Our studies into what we were originally calling ion trap thermodynamics, but it's really sort of more plasma physics, off equilibrium physics. Our detour into quantum chemistry, which has now really whet our appetite to work towards real state-to-state control of chemistry, which I didn't get to talk about. I then told you about our two-stage cooling to make molecular ions. Thank you, guys.
Thanks, Eric. And we have, he was right on time, so we have plenty of time for questions.
Oh, you were scaring me.
Bill.
So the big initial problem was that that this RF quadrupole trap was causing all this micromotional heating, and if I've understood correctly, essentially the solution was to make the plasma more strongly coupled, so that heating didn't occur. I mean, is that the message I should take away?
That's part of the message. The real message is we just laser cooled it really, really hard, the barium ions. So we also trapped some atomic ions with the molecular ions, and it just crystallizes it.
Okay.
But it is true that this heating rate goes way down when the things are strongly coupled.
Yeah.
That's why quantum computation works, because you're doing your gates in the dark. This effect actually sets an upper limit on the longest gate you could do for a given number of ions.
So there's another approach that has been used in the ion community to work with lots of ions, and that is use a penning trap instead of a. So what about that?
Well, so we want to have a MOT, and so we never really thought of a good way to put a MOT inside of a penning
because
trap.
of the big magnetic field would just kill your MOT.
Yeah, you might think of using like a 22-pole trap, something like that, which is more of a box-like potential, but it ends up not helping because you still spend time at the edges and all the bad stuff happens there. So.
And then you might say, well, why not just do everything with ions and do your sympathetic cooling with, but would that then lead to the good vibrational relaxation?
So yeah, that's something I left out, and I should have said, is that because the ions collide basically at really long range, they just don't couple to the internal degrees of freedom.
Yeah.
So you don't even cool rotation, which is usually very easy to cool, let alone vibration.
So I had a question. On this data, which you have there, where you measure the different reaction rates when you put ytterbium in different states, it looked like you don't see a difference from your table in the reaction rates you're measuring?
For the S state is in the few 10 to minus 10.
Oh, okay.
The P state and the D state are in the 10 to minus 9. I purposely didn't give you the leading digits because we just sort of redid this all. I want to make sure we get the right numbers, but that's the order of magnitude. So the P and the D state are reacting basically at Langevin, and it looks like the S state is about 10 times less than that, which is problematic because there are two theory calculations. One sort of agrees with that part, but disagrees with another part of the data, and the other theory part gets the wrong part of the first one right, but the rate wrong on the second one. So it sounds really simple, but it's actually, it's pushing the theorist, I think.
And let me just ask another one then. I confess I didn't understand the potential energy surfaces that you showed for the molecular cooling. What's the difference between the first and the second curve or graph that you showed?
Sure. So this is barium chloride. Looks like my laser pointer is just about to go. This is barium chloride as it would be on its own. This is its bond length of about 5 Bohr radii. And so then you plot here the potential energy surface of the calcium as it comes in with some position R and some angle theta, right? And so you see at about 9 Bohr radii and an angle of 100 so degrees is the minimum. So about the way I've drawn it here. But the global minimum of the complex is different than that. So if you look at the whole volume of the potential over the volume, there's a lower energy solution, which is this bond length has increased a lot, and the calcium has moved in and changed its angle. So this couples the internal degree of freedom of the harmonic oscillator to the external degree of freedom of the collision. And that's what you need to get relaxation. But it should be, I think, fairly general for a lot of molecular ions, because you're going to have a real asymmetric interaction, because one of these is going to be ionized and the other one's probably not.
Okay, so I realize I'm finally missing the bottom line. What's the translational temperature of the barium chloride, and what fraction of it is in the rho vibrational ground state?
Okay, so the translational temperature is that of any laser-cooled atomic ion, because I sort of skipped it, but there's also barium ions right here that we're laser cooling. So, depending on how big your crystal is, it's anywhere from, millikelvin to hundreds, as your crystal grows, right? The internal state, we were only able to accomplish here about something like between 90 and 100% in the ground state. But that was because at this point, our ion cloud embarrassingly was bigger than our MOT, and so most of the time they weren't being cooled. We've now fixed that, and we actually haven't gone back and done this measurement again, but in that case you expect for the current parameters that you'd be in the ground state within about 100 milliseconds of this. It's really quick.
All right. Thanks again, Eric.
Mm-hmm.